Welcome! It is finally time to begin discussing time dependent perturbation theory. Now, what this is, this basically means that we will be dealing with perturbations to a system that will have a time dependence. And why is this so important? Why does this stand out? Well, the reason is that so far, everything we have been dealing with in quantum mechanics hasn't really depended on time. Nothing has been changing. It was always stationary states. We could find the energy of stationary states, stationary wave functions, everything was stationary. And the big reason for that is, of course, that we separated the Schrödinger equation into the time-independent version, and we worked with that. So what we will do now is find a little bit of a technique to work with a very particular case where there is a time dependence, and we'll be able to find some very interesting results. Even through the simplicity of what we will do, we will be able to finally understand some phenomena like the spontaneous emission, for example, and we will be able to understand transitions within energy systems. So this will be very, very, very interesting. Now, to begin, let's of course go back to what we know. We know that the Schrödinger equation, okay, this is the time-dependent Schrödinger equation. We haven't really been working with it too much. We know that we can have it like this. Now, so far, we have of course been working with separation of variables. So what we did previously is that we said, okay, we have a spatial part, and then we had the time dependence, which is minus I e t over h bar. So that is what we are used to. Now, we will only be studying for now two-level systems. So that means systems where we have two possibilities. So we have our wave function, which is going to be, now this depends on both r and t, of course. So this will be some constant, right? Some c. We have ca because we have two levels, so we have two different constants. So I will label one ca and one cb. So ca times some wave function psi a times its time dependence, so minus I e a t over h bar. And then we have a second one, so cb psi b e to the minus I e b times the time part and over h bar. Okay, so this is just this general way of writing down any state where there is some sort of time dependence. But now let's go into specifics. So what we want is we want to have some sort of perturbation, and that can have a time component. So we will write our Hamiltonian as usual, so some unperturbed part plus some small perturbation h prime. So in this case, our solution to the Schrödinger equation, right, our wave function, it will of course have a time dependence now, and we have to consider that this part right here and this part right here, since they are solutions to the Schrödinger equation, they are a complete set. They form a complete basis. And that means that we can write any other function in terms of a linear combination of these functions. So that means that we can take some ca times this plus some cb times this and form any function that we want. However, since now there is a time dependence, we have to open up the possibility that our constants ca and cb can also depend or have a time dependence. So let me just write this down. So basically we just include the fact that now that we have a time dependent perturbation, these constants can also depend on time. And what is something that could happen, for example? Well, we could have, and we will see that in other videos, that for example at time equals 0, so time equals 0, for example, we begin with ca equals 1, for example, and at time, I don't know, at some other time, so let's say just t2, we can have that ca is 0, and if cb started at 0, we could also have that, for example, this went from a transition, right? So we could have that, and maybe in terms of probabilities, it might be clearer. We can basically have a transition, right? Initially, we had only the first state, and in the end, we had only the second state. So for example, this could be depicting a situation where maybe an electron in an atom emits a photon and changes energy state, for example, or energy levels. That could be something that happens. And of course, well, this is simply an example so that you can kind of see where this might be going. And it's very important to note, of course, that the probabilities, so we have to have a conservation of probability. So that means that our the modulus squared of CA plus the modulus squared of CB, they have to be 1, of course. Okay, so the point of this whole thing is that now we will allow for solutions of this form, all right, where our coefficients can depend or can have a time dependence. So now let's actually, get into this. And so now, as I mentioned, we will be dealing with two-level systems. So that means systems where we have just two different possible states. So that means, of course, let's make sure that we understand this, that our base Hamiltonian, right, our unperturbed Hamiltonian acting on psi A, this will give us the energy of that state times psi A. So this is what we already know. I'm just going to write it down so that we are very clear. And that same Hamiltonian acting on psi B will give us the energy of state B, which is EB psi B. Okay, and of course, these two levels are orthogonal, so the inner product between psi A and psi B is going to be delta AB, right? So it's 0 if they're different states, or they're going to be 1 if they are not. So now let's use this to actually solve the Schrödinger equation. So the time-dependent Schrödinger equation. So we know that h psi, so this is in general, right? So I h bar d psi dt, this has to be true. And now we will allow for h to be h0 plus some perturbation. So now we will turn this perturbation on. So what we will do is we will simply plug everything in here because, well, we already know. We know what h is, right? It is h0 plus h prime. We know what psi is. It is this thing right there. And we can take its time derivative. So we will simply plug everything into this equation. So plugging it in, we get h0 plus h prime, all of this multiplying psi, which we know is CAT psi A e to the minus I a t over h bar plus CB of t psi B e to the minus I e b t over h bar. Okay, and then we have the right-hand side, which is I h bar, and then d psi dt. Well, I'm not entirely sure we can fit this all here, so I'm going to write it like this. So this is equal to I h bar, and now we take the time derivative of this. Now be very careful because this thing here also has a time dependence. So first we get, because of the product rule, Ca dot psi A, and well, this thing hasn't changed, a t over h bar, and now we get the derivative of this. So we get minus I ea over h bar, and then what do we have? We have, well, everything else. So Ca of t psi A e to the minus I a t over h bar. And then the same thing, but for the CB term. So we get plus CB dot, and everything else remains the same. So e to the minus I ebt over h bar. And then we get minus I eb, right, taking the derivative of the exponential, CB of t psi b e to the minus I eb, let me move the camera just a little bit, t over h bar. So there we go. So this is what we get when we plug everything into this equation. Now, notice a few things. So, well, first of all, maybe let's multiply through. So this whole thing, I'm going to multiply h0 and h prime. So we get h0 times Ca of t psi A e to the minus I eat over h bar. But what is this? This is the same as h0 psi A, basically. And we know that this has to satisfy the Schrödinger equation. So this has to be the same as I h bar d psi A dt. And notice what we have down here. If we take a look at this, that is precisely, so we have I h bar in front, and then we have this part, which is the derivative of the exponential, of the exponent right there, right? And what is important there, of course, well, we have the CA, of course, in front as well. So what matters here is what in this first term that we just saw, which comes from multiplying this and this, we get CA times this part, which is the same as IH bar, the time derivative of psi, times CA, which is exactly the same that we have down here. So the point is that because of the Schrödinger equation, right, of this whole h prime I is the same as IH bar d psi dt, this first part, when you get the h0 with it, so this part is precisely the same as this part right there. Okay? I'm going to explain it in another way in case you didn't understand when this happens again. So then we have the next term, which is h0 times CB. So then we get plus, and I'm going to change the order to explain it in a different way. Then we have h0 times psi b e to the minus I e b t over h bar. But what is h0 psi b? Well, we know that h0 psi b, right, again, because h0 psi b, this is e b psi b, or we can write this as a IH bar d psi dt. In this case, this notation is precisely what we want. So let's write it like that. So instead of h0, we write it as IH bar d psi b, I didn't add the b there, dt. But what is this derivative? Well, that derivative, since we have this e in here, so it's all of this, right? The derivative simply gives us this minus I e b t blah blah blah. So we get precisely this part right there. So whichever way you want to rationalize it, that part and that part will also cancel out. Okay, so that means that all that we are left with in that second part is going to be, so well, there's still some additional terms here that I will, so we still have to take a look at this times this, and that same one times that. So that's what we'll add now. So this part, basically we still have to add, so maybe let's not put this equal sign just yet. So there we have h prime ca of t psi a e to the minus I a t over h bar, and then plus cb of t psi b e to the minus I e b t over h bar. And there we go. Now we have these two terms and also what remains up there. Okay, so what exactly is it that remains up there? So let me just rewrite this. So all that we have left now is, let's see, so we have I h bar. Actually, I'm going to write it the other way around because that's the way we had it before. So we have h prime ca t psi a e to the minus I e a t over h bar, and then we get the other term, which is going to be plus, let's see, this one right there. So that is, wait, where's the h prime? I almost forgot to write it down. There we go. And then we have h prime c b of t psi b e to the minus I e b t over h bar. And all of this has to be equal to what we have left there. So that is I h bar, and then we have ca dot t psi a e to the minus I e a t over h bar, and then we have plus cb dot t psi b e to the minus I e b t over h bar. There we go. So this is what we are left with after we plug everything into the Schrödinger equation. So again, what we did is we said, okay, let's allow for the fact that our constants of these constants that we had in front, they can now depend on time. So that's what we did, and we also plugged in the fact that we have a perturbation h prime. So by doing that, we get what we have right here. And why is this in any shape or form relevant? Well, because this will, what we basically want is we say, okay, if we turn on a perturbation, we want to not only know these constants, I mean, that's what we want, but we want to know how they're going to be changing in time. Is there going to be a transition or something like that? But here we have not only the constant itself, but also its time derivative. So we will end up with a differential equation which we'll have to solve. Now, how do we go about this? Well, in order to solve this and to be able to actually get to some nice formulas, what we will do is we will use the very famous trick where we multiply by, well, we can do two things. We can do it either by psi A or psi B. Each one will give us a different equation, and we will actually need both, so we will do both. And then we integrate. So we multiply by the bra of psi A. So let's do that first. So first multiplying by the bra of psi A and integrating, or rather, I guess that this notation is kind of redundant. So either multiplying by psi A conjugate and integrating, or simply by the bra of psi A. I guess the integral was a little bit redundant there. And of course, writing this state as the ket of psi A, we get the following. So we get, let's see, Ca of t, that's a constant, so we can take it out of the integral. There's not going to be any space, there's not going to be any x, y, z, theta, rho, none of that. And we can also take this e to the minus blah, blah, blah. We can take it out of the inner product. So we get psi A. The h prime is still in here, of course, because we can't take it out of the integral, right? This is going to be a spatial integral, and the perturbation can very well have a spatial component, so we can't just take it out. And then psi A. And then e to the minus I EAT over h bar. Now we get the next term where we also have CB of t in front. Then we have psi A, h prime, psi B, and then e to the minus I EBT over h bar. And now on the right hand side, it's going to be quite similar, but this time there is no h prime. So that means, so we get I h bar, Ca prime, so all of these constants that don't depend on space. And then we have bra of psi A, which is simply 1, right? So there's no need to write it down. And then we have e to the minus I EAT over h bar. And finally, we have this term, but the last term will have psi A, psi B, which we know is 0. So that's why we don't really need to worry about it. And that's actually the whole point. That is why we did this. Right? This is a very common trick. So now, what is our goal? Well, our goal is to find this thing right there. Because if this is going to be a differential equation, having Ca dot equal to something is going to make it quite simple to solve. So what we will do now is isolate it. So basically divide by I h bar, or in fact, I will multiply by I and divide by h, but it's the same in the end. And also multiply by e to the plus I EAT over h bar. So by doing that, we get Ca dot as a function of time. This is going to be, now let's see, we have CAT, so we have, well, first of all, we multiplied by I, so we get I, then a minus sign, because, you know, from here we got a minus sign, we multiplied by I, and then we divide by h bar. So there we go. Then we have Ca as a function of time, and then we have this thing. Now let's use a notation that we have used in the past, which is basically, let's call h prime ij. This is going to be psi I, if I'm using this arbitrary notation. So psi I h prime psi j. So this is just shorthand. You don't need to use this notation, but you know, it's quicker to write down. So h prime a, so since both are a, we get a, e to the minus I EAT over h bar times e to the plus I EAT over h bar. So that part just cancels out. And then we have, let's see, then we have the second part. So we get plus CB of t. This thing is now h prime of AB. And then we have e to the minus I EBT over h bar. And then we have e to the plus I EAT over h bar. So here we can factor this a little bit. So we can write it as, let's see, put our constants to the front. So minus IT over h bar. And then we have EB minus, so we end up with a positive, EA. So there we go. And that is actually the result for the first part. So that is our first differential equation that gives us CA, or at least that will give us one of the constants of integration. Now we will do the exact same thing that we just did, except that instead of multiplying by the bra of psi A, we do it by the bra of psi B. So by doing that, let's see, I'm going to change colors now. We get CAT, and then bra of psi B, H prime, ket of psi A, e to the minus I, and well, this hasn't changed. Then we get the second term, which will be plus CB as a function of t, and then bra of psi B, H prime, ket of psi B, and then we still have e to the minus I EBT over h bar. And then we have this second part there. However, in this case, the psi A part will be 0 because we get bra of psi B, ket of psi A, which is 0. So we don't have to worry about that part. So all we have left there is IH bar, which is in front, CB dot of t, and then we get bra of psi B, ket of psi B, so inner product of psi B with itself, which is 1. So we simply have e to the minus I EBT over h bar. So here, just like before, we will solve for this CB, the derivative of CB as a function of time. So CB dot, this will be minus I over h bar times all of this. And of course, we also multiply by the inverse of that, or we divide by that, as however you want to see it. So we get CA as a function of time. And now using our notation, that inner product is simply going to be h prime BA. And then we have e to the minus IT over h bar. So I'm factoring out just like I did before. EA minus EB, right? So it's the reverse as before. And then we have plus CB as a function of time times h prime BB. And then we have, well, and this exponent is the same as that, so they just cancel out. Okay, so there we go. This is our result this time. So these are our two important formulas for now. However, luckily for us, and we will see many cases of this, so now I'm just going to state this, but in the next few videos, I will prove this several times over, so don't worry. Something that will happen very, very, very often is that both h prime AA and h prime BB end up being 0, because we will be dealing with a lot of problems like the hydrogen atom, and this is true in that case. And again, I will show this very, very soon, so don't worry. So that means that our notation will actually be much simpler. So what we will end up with, if we apply that, is that CA dot as a function of time is going to be minus I over h bar times CB as a function of time, h prime AB, e to the minus IT over h bar, EB minus EA. And similarly for CB dot, we get minus I over h bar, CB, in this case, it's CA as a function of time, h prime BA, and e to the minus IT over h bar EA minus EB. Now here we can simplify our notation if we define omega 0, which will be very useful later. Now, this will end up being this natural frequency, but we don't really have to interpret it for now. At this moment, this is simply something to make notation easier and cleaner. So we'll say, okay, so let's call something, which is omega 0. Again, this name it will have more meaning later, but you could call it X, Y, I don't care, whatever you want, A something. This will be EB minus EA divided by H bar. So that means that we here have e to the minus I omega 0 times t. And down here, we have to include the minus sign in order for us to get that. So we end up with e to the I omega 0 t. So there we go. These are our two important results. This is what you need to know in order for us to continue with the course. And we will in the future show you how exactly you can use this, and we will continue to develop this method until we find some very, very astonishing results. And you will see that very shortly. So I hope that this video was useful to you. If it was, please consider leaving a like on the video, commenting and subscribing, and maybe even checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.